Hello class, this is the video for section 5.2, one-to-one functions and inverse functions. The following are our learning objectives. At the end of this section, you should be able to determine whether a function is one-to-one, obtain a graph of the inverse function from the graph of a one-to-one function, verify an inverse function, find the inverse of a function defined by an equation. Okay. So let's start with the definition. It says that a one-to-one function, remember it must be a function and a one-to-one. So a one-to-one function, a function is a one-to-one if any two different inputs in the domain correspond to two different outputs in the range. Okay, that is if x1 and x2 are two different inputs of a function f, then f1 the function values at f1 and f2 must be different. Okay, but remember a function is the one that for every input that is corresponds to exactly one output. All right, so a function could be a function but not a one-to-one function. All right, so for the following mappings, all right, which ones are one-to-one and which ones are not, and why if they are not? Okay, look at the first mapping. For every input x1, x2, x3, that corresponds to exactly one output. So that's a function, but the outputs are what are different. Okay, they are not the same. So the first one, there's a domain, that's a range, and that is a one-to-one function because each x in the domain has one and only one output in the range. That is different. Okay, then let's go to the second one. All right, even though it's a function, so this a function is one-to-one of A. The B, it is a function, but it is not one-to-one. Okay, as you can see, every input in the domain has exactly one output. But this one basically is not a function because y1 and the y1 has what two domains from what x1 and x2. All right, so we say that this is actually, if you want to call this, they call it specifically many to what? Many to one. Okay, let me write down here. Many to one function. Okay. Now the last one, it is not even a function because x1 has what? Two outputs. All right. It is not even a function, let alone a one-to-one function. All right. Now, it said determine whether the following functions are what? Are one-to-one. Okay. Here, it says that A, the following function, the domain represents the ages of 5 males and the range represents a HDL, that's a good cholesterol scores, okay, milligrams per DL. All right, is this one-to-one? Okay, it is not one-to-one. It is a function because every age person has exactly one of the, okay. So, but 41 and 53 correspond to exactly one image, HDL. And therefore, this is a function, but it is not what? One-to-one. Okay, as I explained, 41 and 52, that corresponds to what? The same output, which is what? 35. The second one, now we are looking at the images, the domains and then the range, domains and the range. Okay, we are looking for every pair. Is there any input that has exactly what? One output. Two inputs have exactly one output. Like if you look at -3, 5, -2 is 3, -1 is 1, 0, -1, 2, -3. So there is no input that corresponds to two outputs, or there is no two inputs that corresponds to one what output. So this is what it is one-to-one fashion because every distinct input corresponds to a different what? A different output. Okay. Now, remember a function We have the vertical line tests, okay? Vertical line tests, and we test, this is test for what? A function. Whether a graph is what? Is a function. Now, for a horizontal line test, it's for what? A one-to-one function. Okay, so if you have a graph, and then if you draw a line horizontally and it cuts it more than one, then it is not, it doesn't represent what? A one-to-one function. Okay, now as you can see, if I draw a vertical line through this thing, this graph, definitely it is a function, but it is not one-to-one. Okay, so it said that if every horizontal line intersects the graph of a function f in at most one point, then f is what? It is one-to-one function. Okay, so the following graph, we want to determine whether they determine what? A one-to-one function or not, or they represent a one-to-one function. Okay, we have f of x is equal to x to the 6, and that's the graph. Now, well, of course, it is a function because it passes the vertical line test. However, it is not one-to-one because it does not, it does not pass what? The horizontal line test. So this is not one-to-one. What it's saying is that the output, the input one has the same output, and an input -1 also has the same output. So that is not one-to-one function. So this is not one-to-one. Okay, let's look at the second one. G of x is equal to x to the 5th. Remember, it rises to the top and falls to the left. So that's the graph. Okay, so any vertical line, horizontal line, it's going to intersect it at only one place. And so this is one-to-one function. Okay, so G is what? It is one-to-one. All right, it is a function. It passes the vertical line test and it passes the horizontal line test. So it is a function which is what? One-to-one. All right, now a theorem that if you have a function that is just increasing on a certain interval, then that function is what? It is one-to-one. Because for a function like y is equal to x squared, okay, whose graph is like this, all right, whose graph is like this, it doesn't pass what? It is not, doesn't pass the horizontal line test. But if you restrict the domain, if we consider something like x is greater than what? 0, then of course that graph becomes just this. Okay, it becomes just this part. And then therefore it's going to pass the horizontal line test as well as it's pass the vertical line test. So it's a function and it's one-to-one. If we restrict what? The domain. So that is why this is what is increasing, then of course it is going to be one-to-one. On the other hand, if it is decreasing, which is the other half of the graph, the other half of the graph, okay, this part, as it's decreasing from -infinity to 0, then it is also, it will pass the horizontal line test. Okay. So the question is that a graph of a one-to-one function f and the graph of its inverse function are symmetric with respect to what? The y-axis. Y is equal to what? X. Okay, so we're going to denote a one-to-one function by what? The inverse of a function as this. All right, so f and the inverse, and this what? It is symmetric with respect to the line y is equal to what? X. Okay, so what is happening is that if I have, this is the blue, this is my f of x, this is my inverse function. All right, the inverse, please, I want to make this notation. It is not the same as 1 over what? F of x. Okay, because this is a function, it's a name. It's a name of what? A function. All right, it is not a number. It is not a number. Okay, if it is a number, then if I have 2 to the this to raise to 1, this is 1 over what? It's a reciprocal 1 over 2. Okay, but if you have a function like this, all right, it is not equal to that. So take note of that. So what this theorem is saying is that if I have a graph of y or f of x, all right, this is the line y is equal to x. That is, it passes to the origin. Okay, it is symmetric. That is a reflection. If I reflect this graph of f over the line what y is equal to x, then I get the graph of the inverse function. All right. So let's take an example. It says that the graph in the figure shows a one-to-one function. Okay. Draw a graph of its inverse. Okay. So first we have to draw the line passing through the origin, the line y is equal to x. That's what we need to do. Okay, so we add the line y is equal to x, which is that. Okay, this point is 2 lies on the line, so if you reflect, it's going to be the same point. Okay, but this point, which is 0 1 0, when I reflect it, okay, if I reflect it, it's going to be what? It's going to be that. It's going to be 0 0 1. Okay, this point, which is -2, if you reflect it over this line, it's going to be somewhere. All right. So we have since the points -2, -1, 1 0 are on the graph of f, the points, okay, if you switch it -1 2, okay, this point is a -1 2, and then this will flip that becomes what? And so in other words, you interchange. If it's a reflection in the line y is equal to x, okay, you interchange the coordinates of x and y. Okay, so for example, if you have the point x1 comma y1, if I reflect it in the line y is equal to x, then the coordinates becomes what? Y1 comma x1. So that's what it means. Okay, so that is why the 2 is the same thing, the same point, and therefore if we reflect it, we have this graph. Okay, that becomes the graph for that. Okay, as you can see, it's a 2 is on the line y is equal to x. All right, and then there's this point becomes 0 1 if you interchange them. Okay, and this point becomes -1 2. Okay, in other words, the y coordinate becomes the x coordinate, and the x coordinate becomes the y coordinate when you reflect it in the line y is equal to x. Okay, so here's a definition. Then the question is that we should be able to, if I'm given the function y f of x, right, then I should be able to find the inverse function. Okay, say that if f is an inverse function corresponding from the range of f to the domain of f is called the inverse function. So the symbol, as we mentioned before, this symbol is used to denote the inverse function. All right, and so if f is 1 to 1, then f has an inverse, which is that, and it's denoted by what? Yx is equal to f inverse of what? Is a function. So in the diagram, this is what we have. Okay, the domain, in other words, the domain of what? Of the f is a range of what? Is a range of that. Okay, so this is what? This is your f. It takes the what? The elements in what? In the left to the right, and then the inverse brings it back. Okay, it brings it back to the same. So what is happening is that the domain of what the inverse function is the range of what? Of f. And then the range of the inverse function is the domain of f. Okay. So in other words, for any inverse function, all right, if we compose the inverse with what the f, we should get x. And the same way, if we compose the f with what? The inverse function, you should get what? X, where x is in what? In the domain of this, and the first one is in the domain of what? F. So what is happening is that if two functions are inverses, then this is how we check them. So we check that they are inverses if we do what? We do these two things, 1 and 2. So in other words, if you do the composite functions, okay, of one on the other, you should always get what? You should get x. Okay, we'll take examples and verify. All right, so here is an example. It says that verify that the inverse function of what? F of x, which is 4x minus 7, is this. Okay, so what do we do? If you want to verify, we use the what? The information from the previous what? Slide. And that is, first we need to what? We need to verify. To verify, what you do is that you do f of what? The inverse function. Okay, we should do f of what? The inverse function, which is what? F composed on what? The inverse function f of x, like that. Okay, but what is this? What is my f? So this means that whatever I see, I'm going to substitute what? 1 over 4 x plus what? 7 into that function. Okay, so let's do that. This is give me, okay, f of x is 4 times x minus what? 7. So where I see x, I'm plugging what? The f inverse, which is give me x plus what? 7. Now, as you can see, the 4 will cancel out. So what we have there is basically what? X plus 7 minus what? 7. And that gives me what? X. Okay. Then also, we have to do, we compose the what? The inverse function, that is f inverse of f. Okay. Okay. Which is what? F inverse of f. So wherever I see f inverse, x in the f inverse, I plug in what? F of s. So this is the same as saying that this is what? 4x minus 7. Okay, my inverse function is that. So this is what? 1 over 4. And then I have x plus what? X plus 7. So whatever I see x, I plug in what? 4x minus 7. So this is 4x minus what? Minus 7. Okay, 4x minus 7. Okay, that goes like this. Okay, the parenthesis goes around what? This. So this is my x. 1/2 times 4 times x. Okay, as you can see, it is 1/4. I see that. So that's 1/4 plus 7. No, that again, sorry. That is what I did was correct initially. Okay, so this is x plus 7. So you have that. Okay, now what we see is that this is what? 1/4. And then minus 7 plus 7 is what? So this is basically what? 4x. And then the 4 will cancel, and you have what? Just x. Okay, so here we have verified that the two functions, okay, f of x and f I inverses, that's how we verify. Okay, now our point, the point is that at this point you want to know if I'm given any function, how do I get the inverse function? How do I find the inverse function? Okay, in the previous example, they gave us the f and then the inverse, and they said that we should verify. But what if the inverse wasn't given? How do we determine that? Okay, this is the procedure. Step 1, you let y equal to the f of s, or the function that is given, and then interchange the variables x and y in that equation to obtain what? X is equal to f of y. Okay, this equation defines the inverse function, okay, implicitly. All right. Then step 2, if possible, we solve the implicit function equation here, okay, for y, to obtain the what? The inverse function. And so whatever y is equal to what? The f inverse of what? X. Okay, and then we verify, just like we did in the previous example. Okay, so step 3 steps: let y equal to the function, interchange them, solve for y if possible, and then your y is equal to the inverse function, then you verify. All right, so let's take example. We are given f of x. F of x is equal to 3x minus 5. It said graph f and f inverse on the same coordinates. So the question is that we need to what? First know what this function is. Okay, we want to know what that function is. So step 1, we let y is equal to f of x is 3x minus that. So we obtain y is equal to, we let y equal to that, and then now we switch that. So we have what? Y is equal to 3x minus 5, and then we interchange the x and y. So this becomes x is equal to 3y minus what? Minus 5. Okay. Okay, then we go to step 2. It said that we should solve for what? Solve for y. So we have this equation, 3y minus x is equal to 3y minus 5. So we want to solve for y. Okay, what you do is that you solve for y. Okay, now if I solve for y, this I'm going to add what? 5 to both sides. So I have x plus what? 5 is equal to 3y. Okay, and then we divide both sides by 3 and both sides by 3. All right, so y is equal to x plus 5 over what? Over 3. Now, which is the same as saying that 1/3 into what? X plus what? X plus 5. Okay, and therefore, what is your y is equal to the f inverse of what? X. So that is means that the f inverse of x is equal to that expression 1/3 into what? X plus what? X plus 5. So that's my inverse function. Okay, so then we go to step 3 and verify. Okay, we just did a step 2. Okay, so let me write the f inverse of x is equal to 1/3 x plus what? X plus 5. We did this in the previous slide. I just did the example. So we have this. This is our answer. Okay, so now let us go to this and check. Okay, we're going to check that they are what? They are really inverses, whether we got answers right. If we don't get x for each of them, then it means that we got it wrong. Okay, so what do we check? We check that the f composed on what? F inverse of x is equal to the f inverse composed on the f of x is equal to what? X. So we're going to do each one. So first, let's do f composed on what? F of x. Sorry, f inverse of x. Let me erase so I write it well. So f composed on what? F inverse of x. So it means that wherever we see x, we plug in x in f, we plug in the whole f of x. F inverse. By the way, what are the inverses? Well, let's write f of x here. F of x was 3x minus 5. Then f inverse of x is 1/3 x plus what? X plus 5. So this is the same as f. We plug in 1/3 x plus what? X plus 5. Okay. So f of x is what? 3x minus 5. So it can be 3. Wherever we see x, we plug in the whole of what? That expression. This is minus what? Minus 5. So we're going to put in 1/3 x plus what? X plus 5. So the 3's will cancel out, and we're only left with what? X plus 5, okay, minus 5. So remove the parentheses, we have what? X plus 5 minus 5, and that is equal to what? X. Okay, and then similarly, we do the what? We compose the inverse of the function on what? F of x. Okay, so that means that wherever I see x in the inverse function, I plug in the whole f of x. Okay, which is equal to the f inverse, and we plug in what? 3x minus what? Minus 5. 3x minus 5. So let's see if we get the same x as we got here. So the inverse function is what? 1/3. Okay, in parentheses, x plus 5. So x plus 5, we're going to plug in. This is plus 5. What is x? Whatever we see x, we plug in what? 3x minus 5. So this is 3x minus what? 5. Okay, so that is 1/3. Then that is what this will cancel out. So you get what? 3x. And that is equal to x because the 3's will cancel out. Okay, so we have actually verified step 1, step 2, step 3. We have shown that these two are really what? Inverses. Okay, now let us go to the next example. Okay, we're given a function f of x where x is not equal to 2. Why? Because that is not in the domain, as you can see. Or if you are talking about the graphs, then that's a x equal to 2 is what the vertical asymptote. All right. Okay, this function is 1-to-1. Okay, it's 1-to-1. I said find its inverse and check the results. Okay, find the inverse and check the results. So first we replace y with what? Oh, okay. First we have what? Our f of x is this. Our f of x is x plus 1 over x minus 2. Okay, x is not equal to 2. Now we're going to let y equal to what? F of x. Sorry, equal to f of x. And that is y is equal to x plus 1 over x minus 2. And then what do? All right, we interchange x and y. So this becomes x is equal to what? Y plus 1 over y minus what? Minus 2. Okay, so that is what we got. Then we go to step 2 and then solve for what? If possible, solve for y. Okay, so then we go to 2 and solve for what? And solve for y. So we solve for y. Okay, let me go back. We solve for y by what? Let's do the function towards what? X is equal to y plus 1 over y minus 2. Okay, solving for y, we cross multiply. Okay, and so this gives me x times y minus 2 equal to y plus what? 1. Then let's distribute. So x times y is what? Xy. X times minus 2 is what? 2x. And then have y plus what? Plus 1. So let's add 2x to both sides because I want to bring like terms, all the y's together. Okay, and then we're going to add 2x to both sides. So that gives me xy on this side and about y plus 2x plus 1. Then I subtract y from both sides. So this gives me xy minus y. Okay, that cancels out. And have what? 2x plus what? Plus 1. Then if you look at the left-hand side, we can factor out what? Y. And that gives me x minus 1. Y times x minus 1, that's 2x plus 1. Then we divide both sides by what? X minus 1. Okay, so these factors will cancel out. And now we have y is equal to 2x plus 1 over what? X minus 1. Okay, so therefore, all right, therefore, your function, the inverse function f inverse in terms of x is equal to your y. Okay, the y is equal to that. And that is equal to what? 2x plus 1 over what? X minus 1. Okay, so let's write the inverse function again here. So inverse function is what? 2x plus 1 over x minus 1. Okay, so now we're going to check. Okay, we're going to check the results. Check that this is really true. Okay, so we compose the f inverse on with f. Compose f inverse with what? F. All right, so it means that wherever we see x in what? The inverse function, we plug in the whole of the f. By the way, what's the inverse function so that we can remember that this is what 2x plus 1 over x minus 1. Okay, this is going to require some algebra. All right, so let us write it carefully. So whatever we see x in the inverse function, we plug in this whole expression. Okay, so the numerator will give me what? 2 times x, okay, plus 1 over some x minus 2. And that x replaced with what? The whole expression of f, which is what? X plus 1 over x minus 2. And this is x plus 1 over x minus 2. Okay, so then we need to simplify the numerator and the denominator. So this is, we have to find a common denominator for that. So we're going to write this as what? 2 in parentheses x plus 1 over x minus 2 for the numerator, and then the common denominator will be what? X minus 2 over x minus 2. That is for only the what? Only the numerator. Okay, only the numerator. And then the denominator too, we have what? X plus 1 over x minus 2 minus the 2 times x minus 2 divided by x minus 2. Okay, so that we have a common denominator. And what would that be? If I look at the numerator, okay, the common denominator is what? X minus 2. All right, it's x minus 2. Then the numerator becomes what? 2 times x plus 1, and then plus what? X minus 2. The denominator 2, the common denominator is what? X minus 2. And then the numerator becomes x plus 1 minus 2 times x minus 2. Okay, so now let's simplify that. Okay, if you go to, that gives us, all right, the numerator here, if you distribute it, you're going to have what? 2x plus 2 plus x minus 2, okay, divided by x minus 2. All right, this is dividing, okay, the division sign. Then the numerator here is x plus 1, then minus 2x plus what? Plus 4. Okay, also divided by what? X minus 2. Okay, so if we go to the next step, all right, you come this way. Okay, the next step is that just I get space. So we take this one and then we change the sign and flip that. Okay, the numerator here, this 2 will cancel that. And then you have what? You're going to have minus 2x. All right, that will be minus 2x. What was, oh, sorry, this is 1 because f of x inverse is 1, not 2. This is 1. Okay, sorry, that should be the numerator here. This should be 1, and this should be 1. All right, so that should be 1x. I know that's a correction there, because the f of x, f inverse is what? It's divided by x minus 1, but I wrote x minus 2. That's why I put it 2 there. Okay, so what happened is that the numerator, this expression there will be equal to, you have what? 3x, all right, divided by x minus 2, then divided by, okay, then this will be positive 2. Okay, that will be 3 over what? X minus 2. All right, so that is equal to 3x over x minus 2 times x minus 2 over what? Over 3. Okay, so this will cancel that. And then you have for 3x over what? 3. And that is equal to x. So that will cancel. So you see that gives us that expression. Okay. So this is what we went this way. And then we came back and that way because I needed space. All right, then let's do the other part. Okay, let's do the other part. Now we compose the f with the inverse. Again, what is the f of x? F of x was what? X plus 1 over x minus 2. Okay, making sure x plus 1 over what? X minus 2. So wherever we see the x, we plug in what? This whole expression there. Okay, I'm going to be a little bit organized here. Okay, so this is equal to wherever we see x in the f of x, we plug in that expression. So we have what? Okay, it's going to be x plus 1 over x minus 2. All right, so this is be what? 2x plus 1 over x minus 1. 2x plus 1 over x minus 1. Okay, so then like we did, we're going to simplify the numerator and denominator separately. Okay, right, our division is here. Division sign is right there. And then when you find a common denominator, that would be 2x plus 1 over x minus 1, then plus x minus 1 over x minus 1. So that I have a common denominator. Similarly, for the denominator, you have what? 2x plus 1 over x minus 1. Okay, the minus 2 is x minus 1 over x minus 1 to have a common denominator. Okay, all right. Then that is equal to what? Okay, we're going to have the division sign is here. Okay, so that's be 2x plus 1, then plus x minus 1, all divided by x minus 1. And then here too, we have what? 2x plus 1, then minus 2x, then plus what? Plus 2, all divided by x minus 1. So what happened is that this will cancel, the denominators will cancel out. And then you have what? 2x plus 1 plus x minus 2, sorry, minus 1, divided by 2x plus 1 minus 2x plus 2. So let's simplify that. There's the numerator there. Okay. This is 1. So plus 1 minus 1 cancel. And we give me what? 3x. All right. For the numerator. And then here too, you have what? 2x and minus 2x will cancel. And they have 1 plus 2, which is 3. And the answer is what? X. So you see that we have verified step 1, step 2, step 3, and then we verify that the two are what? Inverses. All right. And then final example. Here we want to find where we are to restrict what? Restrict the domain. Because like I showed you, the f of s is equal to s squared. Okay, s squared is not 1-to-1. But when we restrict the domain, say that x is greater than or equal to this, then we have this kind of graph that we talked about before. So this is a graph. So this will pass the horizontal line test. If you don't restrict that, it doesn't work that way. Okay. So we want to do that and then graph the what? Graph the functions. Okay. Graph the functions. Now let us go to, okay. So the function y, that's this, it's a 1-to-1. Okay, as is given, is 1-to-1. Okay. If it's what the graph is for if it's, let's go backtrack a little bit. F of s is equal to s squared plus 1. That is going to be up. Okay, the graph will go up using the transformation. Okay, the graph will be up by what? By 1. Okay, so you have this is 1 and it's going to go like that. Well, it passes the horizontal line, and that is why there's a restriction on the domain. Okay, this is 1-to-1. So what we do is that we let y equal to f of s. That's a step 1, and then we interchange. Okay, so it is 1-to-1. So restricting the domain of this function to x as indicated, results in a new function that is increasing, and therefore it is also one-to-one. Okay, so consequently, the function defined by what y is equal to this, if x is greater than or equal to, has an what, as an inverse. All right, f inverse of x. Okay, so we're going to go through the steps. Okay, step one, we let y equal to that and then interchange. So we have y is equal to this function. So y is equal to x squared plus 1. So when you interchange, you have x is equal to y squared plus 1, and y is greater than or equal to what? Equal to 0. Now, graphically, this is how it's going to be. This is 1. Okay, if you don't restrict, this is going to be the graph. Okay, for this function. So you see that is also one-to-one. So it has an inverse. Okay, so then when we have this, step 2, we want to solve for what? We want to solve for the y. Okay, from that equation. Now, because y is greater than or equal to 1, only one solution for the function is what is required. So therefore, we have, if you see that we have x is equal to y squared plus 1. And then when we solve for y, we're going to subtract 1 from both sides. So that gives us what? X minus 1 is equal to y squared. And because y is greater than or equal to this, usually we should have what? We should have plus or minus, right? For both sides. But because y is restricted to that domain, there's only one solution, meaning y is equal to just the square root of what? X minus 1. That's a positive side because y is positive, so we are only considering only the positive one. Therefore, what is the domain? So I said the domain. What's the word? The inverse function. The inverse function f inverse of x is equal to what? The square root of what? X minus 1. All right. So then we're going to verify like we did. We want to check that. Okay. The first one, we want to check whatever we see. Again, what is my f of x? F of x is what? X squared plus 1. X is greater than or equal to 0. And then f inverse of x is what? The square root of what? X minus 1. All right. So then when we do this, whenever we see x in the inverse, we plug in f of x. Okay. So that is it. So this is equal to the square root of whatever we see x, we plug in what? X squared plus 1. Okay, this is my x minus 1. So this is equal to the square root of what? X squared plus 1 minus 1, which is equal to the square root of what? X squared. And because there's a restriction, this must be positive. Remember, x is greater than or equal to what? X is greater than or equal to 0. And so when you do this, you should have a plus or minus, which means that we have to take the absolute value of that, and that is equal to what? Is equal to x. Okay. All right. So that is check. Okay, because x is greater than or equal to that. So we found that. Now let's do the second one. Whenever we see x in f, we plug in the function, the inverse, square root of x minus that. So this is x squared. So we have x squared plus what? 1. So we plug in what? Square root of what? X minus 1. And then when you move that, you have what? X minus 1 plus 1. And that gives me what? X. So we have checked that, and then we can have the graph of the two. Okay, so that gives me the graph of the what? The two functions. That's where we say that they are what? They are inverses. The inverse of that of f of s is equal to that, and they are both is a reflection in the line y is equal to x. All right, so that is the end of this section. I hope that is helpful. Thank you.